Hi everyone, I'm Prakhar. And this is Team 35, and we are discussing Chrono, which is the OS level memory tiering framework. So let's move forward. So why we need better memory systems? Because as the demand rises, demand rises, we require more memory, and the DRAM scaling is expensive and limited. So new memory technologies like NVM and CXL have come, and we use them in memory tiering. What is memory tiering? What is memory tiering? In memory tiering, what we do is we define many levels of memories. For example, there will be DRAM or the fast memory, then will be NVM or CXL or the slow memory, then comes the SSDs. So the OS decides which pages will stay in the fast or the slow memory. So a challenge is to identify the hot pages and the cold pages. The hot pages are frequently accessed and the cold pages are rarely used, so that we can accurately place into their tier. Why existing systems fails? So existing systems use counters to determine access frequency, which is coarse grained and it is high overhead, and it is hard to adapt to dynamic workloads. What Chrono does is Chrono calculates captured idle time. It is a timer based application, and it uses the capture idle time for each pages. Like it calculates the idle time for each page. If the idle time is less, it will be a hot page, and if the idle time is more, it will be cold. It will be a cold page. So you are able to determine the degree of hotness and coldness here. So it is a fine grained hotness measurement with minimal overhead. Also, it is adaptive. That is, for example, if the page is uh, assume that the now the hot page is the page which the CIT value is less than 500 ms, but a lot of pages are frequently accessed. Then there will be many pages that are hot. So what we'll do is we'll dynamically adjust the threshold and we'll reduce that threshold to about 300 or 200 ms. So we can again we can capture which pages are hot or cold. NUMA balancing. NUMA balancing is a memory architecture in which every CPU has its own local memory node. So every process will try to take its memory to the CPU it's working on. So how NUMA balancing works? It is I will periodically scan the process address space and I will mark some scan pages inaccessible. So when I access that page, a page fault will occur and the CPU will shift that. The kernel will check the CPU, and if that CPU is not the page's current memory node, the kernel will migrate that page to that CPU's node. So the issue here is that it is a MRU, most recently used policy, and it captures only recency, not frequency. For example, if the page was idle for a very long time and now it was accessed, according to NUMA, it is a hot page, but it is not. It is a cold page. So we have misidentified and we are unnecessarily moving it upwards, and we are wasting our bandwidth. So we require a need for improvement. Why accurate hotness tracking matters is if we inaccurately detect we are sending wrong pages above, which will lower our performance. So we did an experiment by running benchmarks, and what we found was that DRAM pages were highly accessed. Also, the MVN pages were accessed about 20 to 40 accesses per minute, but the top 10% NVM pages, which are the hot pages, they were accessed 5.5 times more. We can see in the graph that the DRAM pages were accessed a lot, but the NVM hot, the difference between NVM hot and NVM cold is about 5 times. So we want to accurately determine the hot pages, so that we could identify these 10%. Existing systems and why they fail. So existing systems, there are three types. First, software page faults. So they determine a page is hot or not using the page faults. It is a LRU mechanism. We have because first of all the pages are scanned every 1 minute, and this is a LRU based scheme. So it is based on recency rather than frequency. So the problem is we are scanning one every 1 minute. I don't know what happened that 1 minute. The page can be accessed 20 times, 40 times, 100 times. I don't know that. If I reduce the scan periods, they will be many page faults and it will have a high CPU over it. Second, hardware access bits, in which every PT has a hardware access bit, in which in this method what I will do is if I access a page I will put that as 1. So the problem here is I'm only telling whether page is accessed or not, but not how often. So it is also a coarse grained mechanism. Third is PEBS counter, in which we use hardware counters which reduce our workload and overheads. But the problem here is that it has a very low sampling size. That is, I can only do about 10 to the power 10 to the power 5 pages, but in reality there are millions of pages. So it only works when the page size is huge and not on base pages. So we use different metrics, that is F1 score and PPR, to determine. F1 score is if more, we have more accurate classification. PPR is the ratio of pages promoted to DRAM versus total access pages in NVM. A lower PPR is better. So when we saw that in Chrono the F1 score was highest and the PPR was lowest. It's great, and we were able to do about 1000 accesses per second with our default page size. That was best among all these systems. Also, in problem with PEBS, when we do with huge pages, we can see the counters are almost stable, whereas in base pages there are many high frequencies. So now I will move forward to Rehan, who will talk about design.
Next, we move to the design aspect of Chrono, where we try to answer the problem of non-uniform access time. That means CPUs, when they are trying to access the pages, they want them to be as close as possible. And this is solved by Linux using a feature called auto NUMA balancing. And on the same NUMA framework is a Chrono architecture based upon. It is a OS level memory management system which came into place due to the modern tiered memory architecture, where we had some faster memories and we had some slower memories and some pages that are very hot. The hotness is defined as the number of times it is being accessed in a particular time interval. So the pages that are more frequently accessed, they are hotter, and the Chrono uses a timer-based scheme to check to find these hot pages and move them to a faster memory. The advantage is that we get a minimal overhead because of the reasons that we will study later when we are discussing how the process of the timer approach works. These are the three main components of Chrono that we'll be studying now. First is meticulous page promotion. So the method that we use here is we unmap the pages that are present in the slower memory. And when we unmap them, we start a timer. And as soon as the process again tries to find these pages, it will encounter a page fault. When this page fault occurs, the timer is stopped and we calculate this difference. This will be called CIT, that is the captured idle time. If this time is low, that means the page was accessed very quickly and thus it is called a hot page. So using this method, we can identify which pages are being accessed more frequently and which are being not. Which and the benefit that we are getting from this chrono timer based method is that of low overhead. Earlier, the methods of counter that we were using, they were more hardware based, due to which the system had to keep probing for finding out how many times a page is being accessed. Whereas right now, the method allows the system to tell us on its own using these page faults. Also, we need to only store two timestamp values, so the space used is very less. And since this is a pure software solution, it is quite portable. The next is conditional page promotion. When we are promoting pages in just a single scan, we cannot be sure that a decision was correct, because it could be that by chance a page which is usually not accessed, it came to be accessed in that particular scan that we were doing. So the solution to this problem is of two-round CIT evaluation. This is the first round, and the pages that pass this threshold, they are sent to a candidate page set. And these candidates again go through a second iteration, and again, if they pass this threshold test, then they are submitted into a rate limited promotion queue. The reason we are using a promotion queue is to prevent migration storms. That is, if a lot number of pages are trying to go into the in the faster memory at the same time, this can overload the system. That's where we are using a queue, and this queue will eventually pass them on in a orderly fashion in a limited, dynamic rate limited order. Next, we move to parameter tuning. Let's say a user provides us with a rate limit, the promotion rate limit. So a Chrono's task is to autonomously tune the CIT threshold to meet this rate. So let's say first we will find the NQ rate that the system is currently working upon, and we will compare it to the limit that the user has prescribed. If it is greater than the limit, that means we are being too aggressive in enqueuing the processes in pages. So we will lower CIT threshold criteria. And if it is the opposite, then we will raise the CIT threshold. This is done with the help of the adjustment factor R, which is defined as rate limit divided by NQ rate. And using this R and delta, we can update our threshold value using the formula that has been given below. The value of delta determines how fast or how intense these iterations will be, these changes will be. Based upon that we will eventually, through a series of iterations, reach a user-defined rate limit as shown in this graph. The advantages obviously are that we prevent underutilization and excessive migrations. Also, this is a lightweight process because we are using only two counters for computation. Next, this is a totally automatic parameter tuning method because not in all cases do we know the workload factor. So the user cannot always give us the rate promotion limit. In these cases, the solution is a dynamic CIT statistic collection, which is a fully automatic and statistic driven engine. How it works is we select a small percentage of pages as victim pages. These will be the representatives. And since we are working on only a small population, this will lead to a low overhead. So we collect the CIT values for these pages using the same two-round mechanism that we studied earlier. We build a CIT histogram, that is heat map, for both fast and slow tiers. The blocks in this heat map will represent the frequency value of those CIT of the particular pages. So we detect overlaps. Overlaps, they tell us that if we find that in slow tier memory, there are a lot of significant number of hot pages. And in turn, in the faster tier memory, we are finding a lot of cold pages. That means there's a problem. And this problem is the overlap boundary. And thus, we need a new CIT threshold value along with a new promotion rate limit. Next, we know that we need to transfer pages to the faster memory. So to make space for these pages to come there, we need to demote some of the pages. And this method of demotion is proactive. Proactive means that Linux usually uses a high watermark. When this high watermark is when the full memory is triggered, the Linux process will try to evacuate as many processes that will bring us to this high watermark. But process or architecture Chrono uses an extra dynamic buffer, which gives us more number of pages are evacuated, and that depends upon the default scan interval and the promotion rate limit. Now, these cold pages that are selected to demote it is based upon an LRU strategy. Second is the problem of thrashing. Thrashing means a page that has just been evacuated wants to re-enter the faster memory. That is, when it was demoted, we will detect it using a demotion flag. And in the next iteration, when we calculate CIT values, if we find that the page is re-promoted, then this is a thrashing event, which will be identified using this demoted flag. So the response will be that we will calculate a thrashing ratio. That is how many thrash events happen in all these promotions. If this rate is greater than 20%, that means there's a problem of thrashing, and we have to counter it using by reducing our promotion rate in the next cycle, which will be reduced by half. The final topic is the huge page support. That means most of our pages are 4 KB sized. But let's say that one page is 2 MB, okay, which is 512 times this page. Now, when we run the scan of CIT, we find that this page has more chances of getting an excess hit, due to which it will be falsely identified as a hot page. And to counter this problem, we have two solutions. This is a direct solution. That means that if this page has a larger memory size, it is bigger by a factor of 512. That means the threshold formula, the threshold value of its CIT should also be lesser by 512. And similarly for gigabyte pages, we will again extra division of 512 will take place. The A different method to implement the same strategy is that of normalizing DCSC statistics, where we take the same heat maps, and this time for a huge page we count it as 512 base pages, and we place this in the bucket of I plus 9, which compensates for the 512 frequency factor here. And this will help us achieve the frequency equivalent normalization, and in turn we will get a fair statistical tuning. So this result will prevent over promotion of underused huge pages.
So my friends already explained the design of Chrono. Now I will explain the section 4, which is all about how they actually made it. The main thing to understand is that Chrono is very practical and very lightweight. It doesn't use lots of resources. First is the kernel integration. This is how they really built it. They put it directly into the Linux kernel 5.18, which took them about 1900 lines of code, and it's easy to switch on because they added a new pneumatizing option in sysctl. And like, what is sysctl? Sysctl is just a simple command in Linux that lets you change the kernel setting while it's running, so you don't need to recompile the kernel to turn on and off the Chrono. Now the best part of the this is memory footprint. How much the RAM does it uses? This is always the big problem. But Chrono is like tiny. Their metadata and extra info it needs is just around 4 bytes for every single page. So the total extra RAM it uses is 0.2%. Even the list of key hot pages it keeping is less than is taking less than 32 KB memory. Now let's see the parameters. Scan step here is 256 MB. This is means it checks the memory 256 MB at a time, and the scan period is 60 seconds. This means it tries to check all of the processes memory once every minute. P victim is 0.003%. This is the most important for auto tuning. Like victim is what? It's just the name for the pages they choose to test. This means Chrono only tests 0.03% of the memory. Let's say if memory is 256 GB, then it is just 8 MB of data. And here we choose buckets as 28. Bucket is what? Like it's just like a basket. And when a Chrono measures how hot a page is, it puts into the one of the 28 different basket from very hot to very cold. This helps the Chrono to build a picture of whole system. So now move on to section 5. This is like evaluation where they prove that how that Chrono actually works. First is what type of hardware did they use? They took a server and made two memory tiers. Fast tier with a 64 GB of normal DRAM and a slow tier with 256 GB of Intel Optane. This is 1 is to 4 ratio is common nowadays server. So now let's go to the comparison. Who did they compare against? First is the baseline is just your standard Linux NB NUMA balancing. Then other new systems like auto tiering and TPP. And main competitor here is Memtis, which is important because Memtis uses huge pages, not small pages. And finally, towards the benchmarks, what test did they run? They used PM Bench for checking basic speed and Graph 500 for graph work, and even real apps like Memcached and Redis with a 160 GB dataset. So a very thorough testing they did. Okay, let's look at the result. This is from PM Bench. The workload was 250 GB test with a skewed pattern. By means, some pages are used a lot and most of the pages are used very little. Now look at the performance gain into the graph. Chrono was like around 3.16 times faster than the standard Linux. This is 216% improvement, and it also beats all the other systems. So question is why here Chrono is winning. It's all about being accurate. Like this workload has an access frequency of 1.14 times per second. chrono timers Chrono's timers method like can easily see this, but the competitors are blind. By blind means their scan window is around 60% 60-second long, and for them a page is accessed two times per minute or 100 times per minute. Both are just hot. like both are same, and Chrono can see the exact difference between their hotness, how hot the page is. So we concluded that throughput is good, but what about the latency? Latency is what the user feels and how fast the system responds. And here Chrono is winning also. Like look at the improvements. Average latency is cut by 68% and the median latency is cut by 70%. But the most important number is P99 tail latency. This is the worst case lag. Chrono reduces this by 79%. This is huge improvement, and here the main point is all about to being consistent, because Chrono is so accurate, it makes sure that the correct hot pages are always in the fast DRAM, and these stops like painful slow moments for which like user hates. The other systems, they are not so accurate, like so sometimes they are making mistake and you get a big lag. So this slide is the basically proof. It shows why Chrono is so fast. We are looking at a metric called FMAR. This is simple. Like it just asks what percentage of memory access actually went to the fast DRAM. And the results are like they are very impressive. Look at the baseline Linux NP, only 49%. That means half of your access were going to the slow memory. And the other competitors are also stuck at 50s and 60s. And look at the Chrono, it is way up at 77%. So the analysis is clear. This is like it's proof. Chrono is very careful measuring and it's working very uh, uh, like better than other systems. It finds that correct hot pages and moves them into the fast DRAM. This forces 77% of all requests to be served by fast memory, and these 28% jump from the baseline is like the reason why it is so much faster. Okay, but what is the cost of all this performance? Like nothing is free. So this is the explanation. The performance equation is simple. You get a 77% FMAR, plus you have a very small overhead, plus you reduce bad decisions. Like, and all this gives you around 2 to 3 times of speed up. Let's look at the kernel overhead. This is CPU time used by kernel. Auto tiring is very very expensive, 14.1%. The Linux baseline is 6.4% and the Chrono is only 8.5%. This means it only adds 2.1% extra overhead to get all these big achievements. It like very efficient. Now look at the context switches. This is the number tells you if the system is thrashing, let's say, making a lot of bad decisions and moving pages back and forth. So the Linux baseline is doing this a lot, like 335 switches per second. Chrono reduces it to 241. So the conclusion has 2 points. First, Chrono has a winning plan. Like it also adds a small 2.1% of overhead, kernel overhead. And second one is a small cost pays off big time, and because it stops all the bad page movements and cuts context switches by 28%. Okay, this is my favorite slide. Like I called it as money slide because it shows the main point so clearly. The test was very important. They ran like 50 applications called C groups at the same time. They set up C group 0 was super hot and C group 49 was very cold. This is just like a real server in a company with many users. The fail of other system is what? Look at the top graph. Every other system like Linux, TPP, and Memtis completely failed. They are blind. Like they can't see which app is hot and which app is cold. So they just gave every app same 25% of the DRAM. This is not smart. Like and now let's look at the Chronos graph. It's perfect. Like it's correctly show the hotness, and the hottest app C group like C group 0 got almost 100% of its memory in DRAM, and the coldest app they were moved to the slow tire memory. These frees up the fast expensive DRAM for the app that really needs it. Like this is a huge win for the fairness and performance. Now Samir will continue.
Now we move on to real world simulation. Your 160 GB dataset was used on Memcached and Redis. Get and set operations were performed. As we can see in the graph, Chrono, the green bar, has the highest throughput in both the workloads compared to other processes. The major failure of other processes, first cause was coarse-grained policy failure. Other systems did not have a high frequency resolution for traffic. Second major problem was huge page bloat. Other processes like Memtis use 2 MB page granularity, which leads to high page system, leading to memory bloat. Moving on to design validation. When designing, the first challenge faced was of transient access. The single round hot page is very vulnerable to random accesses and noise. To tackle this problem, we designed the design uses a filtering system to promote hot pages based on their frequency. The design contains a validation of two round filtering. As we can see in the graph, Chrono Basic single round filtering has significantly lower throughput than Chrono Twice ping bars. On the other hand, when we move on to Chrono Thrice, the red bars, they have stagnant throughput compared to Chrono Twice. Hence, to optimize ourselves, we'll restrict ourselves to Chrono Twice. Another observation is that the green bars, Chrono Full, has highest throughput in all the ratios. Chrono Full achieves the highest throughput and lowest migration overhead. As we can see in the CET threshold graph, the threshold is very high initially. It drops very fast and becomes stagnant around 200 milliseconds, which is equivalent to the upper bound of access intervals for the hottest pages. Another graph over here is rate limit stabilization. Rate limit also started very high, around 600, and then it started reshaping it very fast. And when it reached a low value, it stabilizes and retains its shape. When we talk about other methods, they are either focusing on platform CXL or optimizing their mechanism for migration. When we talk about Chrono, it is orthogonal to both platform CXL and mechanism migration. Hence, optimization optimizes our throughput. Chrono is a kernel level policy ensuring applications transparency and general applicability. Chrono breaches OS intelligence and hardware heterogeneity and hence is orthogonal to policy hotness decisions too. Chrono consistently outperforms state of art in both synthetic and real life applications. Chrono is very fine grained compared to other any methods we have discovered. By using the 4 KB page granularity, it also avoids the page bloating problem. The reason why Chrono has a better throughput are its four pillars. Pillar 1, meticulous hotness measurement. Pillar 2, stable page promotion, the two-round filtration process. Pillar 3, adaptation and transparent tuning, the TCSC mechanism of stimulating pages for reducing migration ratios. Pillar 4, proactive management, promotion aware watermark and thrashing monitor maintain fast tier availability. When we talk about the strengths, Chrono's strengths lies in its precision without cost. It's a timer-based CIT, measures the page access frequency extremely finely, about 1000 accesses per second without any overhead. Huge page fix, it uses a very small 4 KB page where, compared to other methods and has nearly no overhead. On the other hand, Chrono is also self-stable. Two-round filtration process avoids false migrations. DCSC mechanism keeps tuning thresholds automatically. Together with a thrashing monitor and watermark, Chrono manages memory proactively. But Chrono has its own limitations. On huge page competitions, it is beaten by Memtis. Memtis is 1.03 times faster than Chrono in huge page competitions due to addition of slight overhead by Chrono. When it comes to restrictions, Chrono still depends on external parameters like scan step and scan period, and its thrashing threshold is fixed on 20%. Those may need better automation. Lastly, because it's built on Linux, it has complexity in its architecture. Possible future works for Chrono can be faster migration mechanisms, things like batched or huge page aware transfers. It is also an ideal candidate for CXL and disintegrated memory, where DRAM and NVM are shared across servers. On the policy side, we can push further, extend to multi-tier hierarchies, and generalize hotness tracking for virtualized and cloud environments. That will be the wrap up for our assignment. Thank you.